So what is hardware engineering? To define that, we need to understand what is hardware. Hardware is an entity that we can interact with. And we have a bunch of examples on our right, ranging from heat sinks to motherboards, processors, and power supplies. The design, development, and testing of hardware is termed as hardware engineering. And lately, I think this is something you would realize, that the usage life expectancy of hardware has increased manyfold. Consumers and companies alike expect hardware to last for a really long time because the focus has shifted towards software to introduce multifunctionality. You would face this debate soon enough, hardware versus software, and you would be expected to pick sides. So is hardware important? We need to ask this question before actually choosing hardware engineering as our career. And at the risk of answering this question with a question, let me ask you, how many times has software versions changed on your mobile phone? Maybe a couple of, depending on whether you use Android or iOS versions, your phone would have probably gone through a bunch of software updates. But how many times did you change your phone for that? How many times has software versions changed on your computer? It's very possible that you used one laptop which underwent an OS change from Windows 7 to 8, probably even 10. Satellites nowadays have communications to ground stations to update their software. But I don't think anybody calls NASA just because they want some guy to go up in space to fix their satellites or to do a repair on that. And another interesting analogy that I like to use is that of your own body. You're learning something right now, and that means it's sort of an equivalent to undergoing a software upgrade. But how many times has your heart changed in the last 10 years? I'm hoping never. And I wouldn't even wish a heart transplant on my worst enemies. So bottom line is, hardware is really important, equal to, if not more than software. And good hardware and good software need each other for a good marriage. Hardware engineering can be broadly classified into two categories. Number one is embedded system design, where you design a system with a brain, a microprocessor, which carries out instructions and tasks and computes for you. In this choice of a career, you would be designing processors, RAMs, serial COM chips, and some other ICs, also including a combination of all of these elements. And the next one is electrical system design, where you can design systems which interface with other systems, like mechanical or software. Components which you will be associated with in this type of a design scenario are batteries, motors, alternators, and cables. Normally, these two fields do not overlap. There is not one designation which tells you that, okay, you need to do embedded system design for me, and you need to also do electrical system design for me. They are usually separated, and a person tends to choose one over the other when deciding their career. So if we were to look at this category division that we have done from a vehicle's perspective, you will either design the engine control unit, which is an embedded system, or you will design the complete architecture of a car, which is electrical design. And I hope that I've made this distinction clear for you guys. So regardless of whether you're designing circuits for a PCB or circuits spanning a car, you have to abide by a few responsibilities, which are summarized below. And the timeline of these responsibilities is pretty intuitive to understand why one is mentioned before the other. So let's just go through the list and see what they are. The first responsibility that you as an electrical designer or an embedded system designer has to fulfill is to design the schematics. So once you realize what the product needs to do, you need to design the schematics for all the circuits. The second responsibility that you have is to select the components. Select the resistors, select the capacitors, select any other IC that needs to be on the board, or select batteries and motors and alternators that we talked about. The third responsibility is to analyze mathematically and through simulation whether your circuit does what you think or what you intend it to do. The fourth responsibility that you have is prototyping and testing the circuit, which is pretty important because now you've done the simulation and you need to actually make a real life version of the circuit and see if it behaves the way you think it should behave. And all of these responsibilities actually lead to the biggest responsibility that you have, proving that your circuit works for production. Nobody is going to spend money on your circuit if you cannot prove that it's going to work, which is what a company is going to shell their money on. I will explain in detail some steps to follow to fulfill each duty in future slides. To drive the message home, let us consider a very simple example of a circuit, LED driving circuit, your hello world equivalent in the electrical and electronics field. Consider you're working as an electrical designer for a prestigious auto OEM. And OEM means original equipment manufacturer, companies like Mahindra and Maruti and Suzuki. So let's say you're working as an electrical designer for a prestigious auto OEM, and your project management team approaches you, notifying you that they have benchmarked some new car in the market, and they really love the idea of a LED under the hood, indicating that the hood is opened. Hood is also, I think, referred to as bonnet in India, if I believe correctly. So the project management team tells you that they benchmarked some new car in the market, and they really love the idea of a LED under the hood, indicating that the hood is opened. And they want this idea for the new car project that you've been working on. So you are the designer, you jump on board, and you produce the circuit on the right. So right here, we have a circuit, a simple voltage source, a resistor. We will see how we derive the value for that, and an LED, no biggie. So you know your responsibilities, but not completely. So you design the schematics, and you choose a LED with the specifications as mentioned. So here I have chosen an LED which has a forward voltage of 3.5 volts, a forward current of 20 milliamps. We move on to calculating the current limiting resistance, and we arrive at 75 volts. The question to ask is, do you give an okay to this circuit for production? You don't do that because you did not follow all your responsibilities. But what would the consequences be of not doing that? Let's have a look. Well, what are the things that you did not consider? The first thing you didn't consider is the environment. What are the thermal and mechanical properties of the surrounding area where the circuit is going to be housed? The second factor you didn't consider was the variability in specifications. How do important parameters change as the environment changes? And what about noise? Is your system analog or digital? Does it have any noise immunity at all? Let us just consider environment and variability in specifications as the observational criteria here. So look at just one of the many curves in the data sheet of the LED, the forward current versus ambient temperature, which is shown on the right. It illustrates that as the temperature around the LED increases, the forward current decreases. So what observations can we draw from this? Well, the number one observation is that this LED is clearly unsuitable. Temperatures in the engine compartment can rise to 125 degrees, and 125 is not even indicated in the graph. So this was a bad LED choice. But hypothetically, let's assume that we still went ahead with this LED. We figured out that we didn't actually knew the temperature of the engine compartment, and we still went ahead with this LED. So as temperatures rise to 75 degrees, what is the voltage drop across the resistor? So we can pick up the forward current from this graph right here, and let's assume that the forward current is 5 milliamps at 75 degrees. So the voltage drop across the resistor drops down to 0.375 volts, which makes the voltage across the LED, the voltage that the LED now sees, equal to 4.625 volts, which is greater than the max forward voltage drop that the LED can see, which is shown here in the data sheet. The max forward voltage drop across the LED is 4 volts, and your LED is destroyed. So these are some factors you didn't consider, and your circuit is now labeled as a failure by the project management team. So I hope that I've hit the nail right on the head. Even with a simple LED driving circuit that many of you will design in your life, you have to think and act according to numerous factors which will influence your circuit. And thus it is really important to have a look at the responsibilities again and arm yourself with weapons to make robust circuits. The responsibility of designing a schematic needs you to understand a circuit design tool, and it needs you to understand electrical engineering principles, which you are going to be studying while you pursue your bachelor's or master's. The next responsibility, to select components conforming to design standards, needs you to learn how to read data sheets and scan through them for important parameters and specifications, which can modify the way your circuit behaves. The next responsibility is to analyze the circuit mathematically and through simulation. So for that, you need to understand mathematical analysis, things like Taylor series, things like derivatives and differentials. You need to understand circuit solving, Kirchhoff's law, Thevenin's and Norton equivalent, and other things like DC and transient responses. The next responsibility is to prototype and test the circuit. So for this, you need to understand how to solder. Some basic soldering techniques would be good to know. You need to understand how to work your way around a CRO, multimeters, and logic analyzers. And finally, the most important responsibility is to prove that your circuit works for production. So for that, you need to understand manufacturing processes and limitations. Over your life, you will probably come across terms like Kaizen and 5S and some other Japanese methods that the automotive industry has employed to make sure that their manufacturing process is efficient. So you need to understand all of these. These are big responsibilities and they need to be taken seriously. So lots of responsibilities for just one circuit, and you will design hundreds over your career. I hope that it is not overwhelming, but your responsibilities will never change. And your knowledge will only improve as time goes on. And you will find effective circuit design to be easier when you start it. So don't ever lose sight of the objective. Let's move on and look at what are the current trends or sectors which require circuit design and analysis and are looking for bright minds such as yourself. The first is IC design. If you happen to land a position with a company which is involved in IC design, you would primarily be designing ASICs, FPGAs, and system on chips. If you were to actually follow entertainment systems and recreational gadgets, some products are speakers, headphones, fitness watches and bands, your home control systems, and automotive, which is the industry that we're focusing on. So you would be designing engine control units, body control modules, and the complete architecture. Next is aerospace. You would be designing pilot and co-pilot panels, avionic systems, computers and controllers. And there's, of course, defense. There's missiles and planes and how to actually tune the planes to make sure that they can get involved in defense rather than the commercial sector. There's, of course, railways, which is pretty big in India, so big company to actually be involved with. And healthcare, a field which is in high demand right now, given how we are required to maintain distance from each other. So can you make a product which can eliminate the need for a person to be around another for taking swabs, as we do for testing COVID-19? Power generation. Having continuous or extended periods of power at our houses is becoming a right now. It's no longer a luxury. You need to absolutely have to give your consumers, to give the citizens of the country 24 hours of power supply. Can you build circuits which can work 24 hours a day, 365 days a year? How do you do that? Lots of questions to answer, but this workshop is about introducing you to the field of circuit design and analysis in the automotive industry. So let us familiarize ourselves with the trends in the automotive industry, and let's look at what some of those tech advancements are. So what are the tech advancements which have happened in the automotive? The first is cruise control with deceleration. Cars on cruise which can sense when they are coming dangerously close to another and slow down. Passive keyless entry, which is something that I worked on the XUV 500. No more putting the key in a key cylinder and twisting it to accomplish things. Antenna sense the presence of key in the car and on you go. Infotainment system with interactive vehicle control. You can actually control the actuators in the car from your screen. So you're eliminating a lot of buttons. Semi-autonomous driving. Chill in your car while it drives itself. We are also looking at autonomous driving in the future. Ultrasonic sensing. Use ultrasonic sensors to tell you the distance of your car from an obstacle. Fleets and connected cars. Cars which talk to each other and update about accidents and incidents on the road. And of course, electric vehicles. The future is electric. And I'm not going to argue about that here. I think all of you are smart enough to see it. So there are lots of tech advancements which have been taking place. The automotive industry needs bright minds like you. A car is increasingly becoming a hotbed of electromagnetic waves, and you are needed to make sure that it's safe and secure for a consumer. So let's get down to getting some help now. We need help when it comes to making professional circuits. We cannot be using crude methods like a paper and a pencil while building circuits all the time. So let us look at some application providers who can help us fulfill all these responsibilities that I mentioned before. For embedded systems, you have Altium, Mentor Graphics, and DipTrace. So you would be using one of these applications if you were to actually become an embedded system designer and work on PCBs. Now, DipTrace is an open source PCB design tool, which I prefer to use for two-layer PCBs. For circuit analysis, you can lean on or find help with LT-Spice and OrCAD. LT-Spice is another open source circuit analysis tool that I like to use instead of shelling out large sums for licenses. Very important for 3D modeling and design. So applications like CATIA, PowerDraft, and AutoCAD will help you do that. So trust me, if you are being taught AutoCAD in school, take it seriously. Vehicle harness design. Applications like ePlan and PREE Vision will help you accomplish that. product lifecycle management, which is sort of like a GitHub for hardware designers or hardware engineers. PLM is a repository where you can find all the drawings that the organization releases. Most automotive companies that you work for will employ the usage of almost all of the applications mentioned above. So if you can get started now, it would be good. I'm sure that you will be taught AutoCAD or some form of rudimentary PCB design or electrical design. So just take it seriously if you want to learn it. So it is worthwhile to know, it's really worthwhile to know how these things, well, who they are and what they do. Who are the world leaders in producing hardware to help you realize that the next electrical circuit that you're making for your car. For embedded systems, there are companies like Bosch, Delphi, and Continental. So these companies are producers of controllers, like engine control unit, anti-lock braking system control unit, and other controllers. A car can have many controllers. XUV had 13 controllers when I was working on it. For circuit analysis, you can rely on Fluke, Tektronix, and Yokogawa. They are producers of CROs, multimeters, helping you to debug your circuit. Debugging is an art in itself, and you need to have proper tools to do a good job. For CAD, most automotive companies rely on usually in-house manufacturing lines or very rarely on some third-party vendors. It is really important that as a designer, you produce drawings with standardized design rules because prototyping is a huge expense for manufacturing department. When a product is not being mass manufactured, the cost of producing that product shoots up. So it is really important that your drawing has been checked and approved before it is passed on for prototyping. Additionally, your design will be governed by many standards maintained by regulatory bodies like ARAI or by the OEM itself. Like when I was working for Mahindra, Mahindra had its own design standards for electrical engineers and mechanical engineers. These are design requirements put in place with the safety and comfort of the end user in mind. And they might be derived from years of experience of personnel in that particular field. When you start with an automotive OEM or a vendor, you will be required to study standards for connectors, harnesses, telltales, for communication protocols like CAN, for lighting, and for onboard diagnostics. These standards are the reason why the turn signal lamp of your car is orange or amber, or why the tail lamp is red. These standards govern how you would design the whole vehicle architecture. And you would be required to make sure that you tick all the boxes in the standards, or the car that is produced cannot be certified and cannot be sold in the market. By this time, I believe that you would have understood that hardware engineering is really demanding, and it has lots of responsibilities, and it's not all that easy. So the demand for hardware engineers has failed to plummet. So if you have been moved by this workshop and this lecture and are looking for your career in this field, you can search for the following entry-level designations when it comes to that. Electrical designer. I've already explained what an electrical designer does. You will be designing complete architecture of a car while interfacing with mechanical and software systems. Hardware design engineer, also referred to as embedded systems designer. So you would be designing PCBs and any ICs or anything else which is associated with embedded system design. System designer, an engineer who assists mechanical, software, and electrical engineers alike to solve electrical problems or conflicts while ensuring that the project meets its deadlines. Electrical technician, a more hands-on responsibility, spending most of the time prototyping and testing in labs and workshops. Component engineer, these engineers perform the second responsibility on the bullet points that we listed a while back, of sourcing and selecting components according to design standards. These are the engineers that you will go to if you want some help in choosing some battery or some alternator. Electrical manufacturing engineer, an electrical engineer who guides electrical designers about the manufacturing process and how their design needs to change in order to make it feasible for production. So you have many options to choose from and shape your career. Although if you land a position as an electrical designer, which is the first typical job role that we talked about, you are most likely to have a taste of all the designations mentioned above. So your learning will be immense, because I worked as an electrical designer and I have designed PCBs, I have understood manufacturing processes, I have understood why certain components are chosen over another, and I also understood a little bit of how technicians operate. So that is a good role to start with. When it comes to senior level, you will notice how the designation has a more specialized ring to it. More often than not, you will find the word manager being included in the designation. Some of these are self-explanatory, so I will run you through some unique ones. So, like engineering project manager, it's of course a little obvious what they do. Control system engineer, a little obvious as well. Hardware technologist. This is primarily this sort of a role is primarily responsible for overseeing the development of the next cutting edge technology or tech disruption product from a company. Electrical estimator. You will be responsible for the scheduling and estimating of commercial electrical projects. You will need to have strong commercial acumen when it comes to being an electrical estimator. Product development engineer and lead engineer are sort of the same, where they would be leading a small team for a certain project. So these are the sort of roles that you can expect to be in as you advance in your career. At management level, your thinking has to be revolutionized for tasks which have less to do with electrical engineering per se and more to do with the business of the OEM. As a team lead electrical of a specific project in an automotive OEM, you will be handling resources, which can include time, people, and money. You will allocate time and people and will be responsible for appraisals and performance evaluation. You will also be responsible for conflict management. Conflicts will arise in a project, unfortunately, whether it's between peers or between groups like electrical and software or electrical and mechanical. One is always trying to make their job easier for themselves. A leader needs to be accommodating of everyone's point of view. You will be managing project timelines and gateways. So you need to drive your engineers to make sure that the project finishes on time. Think about two car companies in a battle to produce the first car with LED headlamps. If your company fails to meet the deadlines, then it possibly loses out on many customers who would want cars with LED headlamps. And this doesn't look really well on you. Vendor management. Team leads will have meetings with vendors like Bosch, Delphi, and Continental to oversee their tasks and responsibilities. It is imperative to do so because one car has many vendors working on it. And I will illustrate this with an example. So with so many vendors working on one car, the failure on the part of one to do their job can be catastrophic. Training and mentorship for team personnel, which is probably, in my opinion, the most important of their responsibilities. We talked about the current trends in the automotive industry, and you can see that we've achieved a stage where we are really close to rolling out with autonomous driving. So the team leads need to make sure that their subordinates are well aware of the latest trends in the industry and have the required knowledge and capability to design state-of-the-art systems. Let's bring it all together. Let us consider an actual automotive circuit that I was designing and see how a day in my life as an electrical designer would look like. The circuit that I'm considering here is the starting circuit, the circuit which activates when you slide your key in the key cylinder and give it a twist to start the car. Now, the customer here is the OEM, and let us outline the number of parties involved in making the circuit a success. On the hardware front, we have Bosch. Let's say, for example, we took the engine control unit and the starter motor from Bosch. We reached out to Delphi to give us the harness. So the harness which connects the batteries, the ECU, the starter motor, and everywhere else that power needs to flow to start the car. Let's say we approached Excite for giving us the battery. Let's say we selected Little Fuse for giving us a fuse for protecting this circuit. And let's say we reached out to Key Connectivity for giving us relays. But the parties are not actually limited to only these hardware providers, because there is me, or imagine yourself as the electrical designer designing the circuit. There's the lead engineer overseeing your work and the team lead guiding this project. There are more than 10 parties if you include mechanical, because mechanical has to make sure that the battery resides on some sort of a plate. And of course, manufacturing, which has to manufacture the whole circuit. So there are more than 10 parties involved in making just one circuit a reality. Independent of the company you are employed by, the OEM's starting circuit needs to work. That's it. So driving the message home again, each of the parties that are involved in making the circuit need to prove to the OEM that this circuit will work and it will not fail in production. It's a critical circuit. Nobody wants to actually go inside their car 3 months down the line and find that it's not starting, you expect your car to start all the time. So the team lead will make sure that all the suppliers are producing quality components and are doing local testing on them. So each and every vendor is following the responsibilities that we talked about. The electrical designer, you in this case, sets upon the task of designing the circuit for production. And this time you are familiar with all your responsibilities that we have discussed before. You're not going to make the mistake like you made when you designed the simple LED circuit. So you come up with the circuit. So right here, we have a 12-volt voltage source, which is symbolized as, which is the battery. We have a toggle switch, which is the key that you twist in the key cylinder. We have a 10 amp fuse that, let's say, we sourced from Little Fuse. We have a relay we took it from, which is, we are using the normally open contacts of the relay to power the motor solenoid. And this is a control circuit because the coil of the relay is being controlled by the engine control unit. So what happens is that when you put the key in the key cylinder and you give it a twist, the engine control unit receives an input saying the key is in the key cylinder and the customer wants to crank the vehicle. So the ECU drives this line low, that's the line that you can see, and the relay closes, powering the motor solenoid, and your vehicle cranks. So to wrap everything up, now you're aware of the responsibilities as a designer. And your ultimate goal is to prove that the circuit works. So you come up with a circuit and you approach your lead engineer saying that you're done with the circuit and you want the circuit to be reviewed. So the lead engineer can ask you a bunch of questions. He can ask you, can the ECU drive the relay? Is there sufficient voltage drop across the relay coil to generate enough electromagnetic force to close the relay contact? Does the battery voltage stay above the standard requirements when the car starts? Believe it or not, when you crank the vehicle, a 12-volt battery will dip down to 9 or 8 volts sometimes. And there are design laws in place which say that the voltage should not go down below 7 volts. Does your motor and battery conform to this? Is there voltage drop on the line which is making this dream impossible? Can the fuse handle the peak current of the operation? If the peak current is larger than 10 amps for, let's say, 2 microseconds, can the fuse tolerate this? Can the wires carry sufficient current? Did the wires you choose have the capacity to carry the current that you believe the circuit will consume? And is this circuit proven to last for an extended duration? This is a critical circuit. As I talked about it before, a customer expects his car to start all the time. Have you done any analysis which proves otherwise? If you answer no to any of the above, it's a problem. And as an OEM electrical designer, you must coordinate with all the suppliers to fix it. So that would be the first line. You would be the first line of defense. Sorry. Before the team lead actually comes into play, once you're done with this circuit and the lead engineer asks you all of these questions, if you find that things doesn't work, you need to approach all of the individual hardware suppliers and make sure that they have conformed to all the responsibilities that we talked about. And Little Fuse has not done analysis. You need to approach them and tell them that the fuse is blowing because you have done testing at your end. You're the ones who are responsible. So your responsibility not only is limited to your own circuits, but also to each and every designer who's involved, or each and every party that we talked about who's responsible for making this circuit a reality. So how do you enter this domain? Automotive industry is fun, trust me, but it demands a lot of passion for cars. It is a little, comparatively, although I don't need to belittle it, but it is comparatively an easier industry to start your career with because you're mostly working with DC signals unless you work with electric vehicles, which is a different case. So it's a good industry to start with to actually see your electrical engineering principles shape into a product. Sectors like aerospace and defense or space and even power generation demand extensive knowledge, but are not impossible to go into. So don't let me stop you. Don't let me discourage you from entering into any industry or any sector that you want to go to. But automotive industry is a little easier to see how circuit design can be made robust and how you can actually analyze those circuits to make sure that they are working efficiently. It is an achievement and a reward to witness a machine that you helped design. Even now, when I visit India and I see an XUV on the road, I remember all the blood and sweat put into making that dream a reality. And you cannot help but smile when someone else feels pride in owning a car that you helped design. So what do you need to actually enter this domain, which possibly gives you an edge over others? Because sharing my personal experience, when I was having an interview with, I think they could see that I was really passionate about cars, because they asked me questions about like ABS, ECU, but I had no idea about ABS because I never actually worked on ABS, but I knew the basics of ABS. And they could see that, okay, this candidate is actually really interested in cars. So passion, definitely an edge. So be involved with formula teams or SAE teams that you have at your university, and see how things, of course, have fundamental electrical knowledge, because passion is not everything. You need to learn almost everything that you can learn at your university, because all electrical engineering principles can be applied to automotive circuit design and analysis. You will learn about transmission lines. The car's electrical architecture is nothing but a transmission line. You will learn about Faraday's law. You learn about Thevenin and Norton that we talked about. Power electronics. Everything that you learn about can be applied to the automotive industry. So any course, any lecture that you like, remember that it can probably help you out when you land a position in the automotive industry. And debugging and hands-on knowledge. Learn how to use a multimeter, which even if it means just testing some voltages here and there, though be careful if you're actually testing voltages in your house, because it can be dangerous. Hands-on knowledge, of course, very important if you're designing circuits on breadboards, and if you know a little bit of soldering here and there. The debugging and hands-on knowledge is a premeditated strike at what it is about to come if you actually become involved with an automotive industry. Because when I was working at Mahindra, I would be running around with a multimeter, just checking if my circuit is proper, and debugging any faults that I would have, that the vehicle would have, I'm sorry. And trust me, it's a real pleasure when you can figure out what's wrong with the car and you can start it. Because there are a bunch of times when prototype vehicles would not be able to start and everybody's scrambling, call the electrical engineer, we need to fix this. And when you come at the workshop and you can figure out what's wrong and you can start the car, it's a real pleasure, trust me. So I hope that this lecture has emphasized well on why you need to learn not only circuit design, but also analysis. And I hope that our little lecture here is a small step in making you a part of a club of better hardware engineers. And that's the end of this lecture, and I will hand it over to Roshan from here.